In this video, we're going to take a look at how the lithosphere grows with time and with distance away from a mid-ocean ridge. We're going to be looking at oceanic lithosphere, and we're going to use this equation here from the book by Turcotte and Schubert. It takes a very highly idealized case of heat flow loss, but we can use laws of heat flow to calculate changes in temperature relative to the depth y of any given isotherm. And that's literally what we're going to calculate. We're going to look at the depth of an isotherm. In this case, it's going to be the isotherm of 600 degrees centigrade. So that is our T of interest, the T with no subscript. And that'll be relative to T naught, a surface temperature of 0 degrees, and T1, a deep mantle temperature of 1300 degrees. So that 600 degree isotherm will be sandwiched between this cold and hot, these cold and hot temperatures. At what depth will it be relative to these cold and hot temperatures? Well, it depends on the age and effectively the thickness of the lithosphere. So we'll take a look at how that works out. To be able to do this calculation, we have to know kappa. That kappa there is given here. It's usually given in units of millimeters squared per second. We've converted that to meters squared per second. We'll do all of our calculations, or most of them, in meters and seconds. And then we have the distance x. How far are we away from the ridge? So the distance from the ridge. I've just made a list of values here. No calculations. Just I want to look at distance going from some very small distance out to 3,000 kilometers. And then over here, I've simply taken that value, multiplied it by 1,000, so we can convert it into meters. So this is the same thing, just in different units. And then we have to know something about u, the spreading velocity. Here I'm giving it in units of meters per year. So it's about 5 centimeters per year. And we're going to convert it to meters per millions of years and then meters per second, as we'll use that in different calculations. We can go straight to the age of the lithosphere. So if we have lithosphere that is spreading at a rate of 5 centimeters per year, or at 50,000 meters per millions of years, how old would it be? Well, we can get that by taking the distance in meters and dividing it by the rate in meters per millions of years. We want that cell E5 to remain constant, so I'll put a dollar sign there, fill down. So the age is going to be a function of distance, and for the spreading rate that we've given, then at 3,000 kilometers from the ridge, we'll be at about 60 million years. If we make things a little bit faster, let's say 9 centimeters per year, then the age would be much younger, right? Almost 33 million years. Right? So we'll go back to 5. So how about the depth? What is the depth of the 600 degree isotherm? Well, we're going to use this equation, but we have to rearrange it. We have to extract this y. We're going to extract the y. It's caught up in this error function, so we need this inverse error function here. So this is the equation we'll actually use. But what is the inverse error function? Well, in Excel, the way we're going to calculate it is we're going to use this this sort of notation that Excel will use to calculate that inverse error function. I've already done it over here, but we can repeat the calculation. So for the inverse error function, it is equal to the square root, SQRT. The square root of what? The gamma inverse function. And we're taking the gamma inverse function of T over T1. So T, our temperature of interest, divided by T1, that deep mantle temperature, comma, two constants, 0.5 and then comma 1. And we need two closed parentheses, and that's how we calculate that, which is also this value here. So now let's get the depth. So the depth is equal to this thing over here. So let's just enter the first part of this product. So we'll just look at everything inside those parentheses. So we have 2 times the square root of kappa, and we're doing everything in meters per second, multiplied by depth in meters, and then divided by the velocity in meters per second. And then we'll close the parentheses on the square root and hit return. So we get that value. Now let's surround it by parentheses and then multiply the whole thing by our error function. And everything in rows 10 and lower, we want to hold constant. So we'll put a dollar sign in front of all the rows that are less than 10, and then we fill down, and now we have depth in meters, or perhaps more conveniently over here, I've already set it up before we started, this simply takes that value, divides it by 1,000, so we convert depth to kilometers. So we can compare depth versus age. What we're going to do here is compare depth versus distance. So how does the 600 kilometer isotherm look relative to distance? Remember, with Excel, whatever we grab on the left-hand side will always be the x, and this will always be the y. So if we want depth on the y-axis, it looks like we should probably take the depth over here, kilometers versus kilometers. I didn't need to make that copy over there. And we will insert an XY chart, and on this vertical axis, we'll put the values in reverse order, and we will select the dots. The dots make it look like data, but we don't really have data. This is a model. So for the marker, we'll have none, and then for the line, we'll take a solid line and make it a smooth line in case our intervals give it some kind of bumpiness. And then we can insert some rows. We're plotting negative values there. Sometimes Excel likes to do that. We don't really need that. So we'll tell Excel just to stick to the positive values. And we'll make this all a little bit larger so it's easier to read. And we'll increase the size of the axes here. Oh, I forget whether we used 18 or 16 for the other. Let's add some axes. So we'll have a primary, vertical, and horizontal axis. What is the value here? This is x. This is distance from the ridge. Well, let's make that a little bit larger so we can read it. And then this is depth in kilometers. Probably should have put the units on here. This is also in units of kilometers. And the depth of what? Well, in this case, it's the 600-degree isotherm. Let's give it a sharper line, at least a darker line so we can see it a little bit better. Oh, it just wants to color in one segment because we were too careful about how we double-clicked on the line. Well, close enough, not perfect. So what is this? Ignoring the sloppiness in the graph, this is the depth of the 600-degree isotherm for the case that at the ridge over here at 0, so that's the mid-ocean ridge, that temperature is 0 degrees at the surface, and then that the mantle down at some great depth down here is at 1,300 degrees. If we wanted to know a 200-degree isotherm, we could just simply substitute in 200 for 600. And so now you can see the axes have shifted. So now we have the depth at 200 degrees. If we think that the base of the lithosphere is at 1,300 degrees, we can put in 1,300 degrees, and there's our isotherm. Well, that's not very interesting, is it? Let's put in 1,200. So there's our 1,200-degree isotherm, where Excel doesn't go too crazy with the axis. Well, of course, things are going to collapse with the error function. Put in 1,300, then we can't calculate the error function. So it's not just the axes. So if let's say the base of the lithosphere is at 1,250 degrees, it's going to grow at this rate as we move away from the ridge. We can change this distance to time if we prefer, so we can make another chart. Let's just take a copy of this and paste it over here, and we can replace distance. So here we're plotting distance in column C from the ridge. So instead of C, we can have column G. So we'll replace the C with a G. Column G is our calculation for the equivalent of age. And so now instead of distance, you don't need to do that. We don't need to format. This is the age of the lithosphere in millions of years. And so now we have a depth age curve. Either one can be handy depending on what you're interested in, but it tells us how, as we move away from the mid-ocean ridge, which is here at zero age or at zero distance, the older we get or the further away we get, then the deeper the lithosphere is. Why? Because it's losing heat. We're dumping heat out of the system, and so the lithosphere, this cold, thick lithosphere, just gets older and older. In reality, what happens if we actually plot the lithosphere is it actually flattens out. There's a certain depth where, at about 80, 100 kilometers or so, it doesn't get any deeper. So the depth age curve from this half-space cooling model no longer applies. And the reason why it actually flattens out is, we think, is because the mantle is hot enough that the convective mantle would erode this stuff away. And so the half-space cooling model is not the only way to think about how heat is lost. This assumes that all heat is lost only by conduction, but if we have convection in the deep mantle here, that can bring up hotter material from greater depths in the Earth. And so that's a different mode of heat flow, and that would cause us to modify this curve, and is one reason why it would flatten out instead of following this ever steepening path as we show it here. So there are some very definite limits to using this kind of equation, but there you go. This is how the lithosphere, the oceanic lithosphere, at least ages with time. The continental lithosphere would do more or less the same, except it's also going to be limited in its depth by this convective mantle, which will erode the continental lithosphere at the bottom. And these are the equations we use usually to get things like so-called depth age or depth distance curves.